All right, so here is the review video that I promised that I'm kind of lacking behind on. But anyways, so this is the exam video for exam number 3. So let's start off. So first we had work. So this is our first chapter here. So work, now it's actually defined in terms of an integral, but since we're not having integration on this particular exam, so I'm not going to start off with that definition. I'm just going to go with the one for force is equal to a constant. So as long as our force is equal to a constant, in this case, then the work is the force dotted by the displacement, where most of the time we can take that our initial position is equal to 0. So this is going to be the same thing then as the force dotted by simply the displacement. Or in terms of magnitudes, this is the magnitude of the force times the magnitude of the displacement times cosine of the angle between the two. So specifically, as always, if this is my force and then this is my displacement, then it's the angle specifically between these two vectors. So as always, all this basically means is that the parallel portion of the force, so if I broke this out into my parallel portion, so this is the parallel portion of the force is what's doing the work, where the perpendicular portion of the force does not, because it's not in the same direction as our displacement. Good. So next up, we then have our kinetic energy. So we said our kinetic energy then is 1/2 mv squared. And these two guys are related to each other by the work kinetic energy theorem, which simply says that the net work and only the net work is then equal to the change in kinetic energy. So this is not simply for a single work, but it's the total amounts of work which are added onto the system, right? So in this case, again, remember that the network is simply the sum over all the possible works which are acting on our particular system. Now, it may be just from one force, right? If all the other ones actually just cancel out, but typically it's going to be simply this guy. And then other than that, we need to know the work of a spring. So for a spring, we know that the work of the spring is equal to 1/2 the spring constant K times the initial position squared minus then the final position squared. So this is our work done by a spring. So good. And then the last thing in this chapter is the power. So the power P is then equal to the time rate of change of the energy, which is the same thing as the time rate of change of the force, or sorry, time rate of change of the work, which is the force dotted by the velocity, or this is the same thing then as the magnitude of the force times the magnitude of the velocity times cosine of the angle between the two, where just like with the work, we then have, if this is my force, and then this is my velocity, then again, it's the angle specifically between these two vectors. So again, it's a parallel portion of the force, which is creating the power in this case. So again, if I drew that on here, again, here's my parallel portion of the force, which is generating the power because it's what's causing the work, where again, my perpendicular component is not doing anything as far as work and power are concerned. So that's it for this particular chapter. So these are all the things that we basically need. Now, when it comes to work kinetic energy theorem, most of the time you don't have to do this as long as you know conservation of energy, which is what we're going to talk about next. But anyways, the only way you would really have to use this guy here is if the problem specifically states that you have to use it, which there will be one problem associated with that, and I'll talk about that in just a second. So next up, we have energy. So good. So going back to here, what this statement again says is that what? Kinetic energy is the ability of a moving object to do work. So a moving object can do work. So that means that other things have the ability to do work as well, and this is what we call potential energy. So potential energy is, again, by its definition, it says that the change in potential energy is minus the work done by the conservative force, right? So again, a conservative force, as far as we're concerned, is basically gravitational and spring. Everything else basically will come in as a non-conservative force. So that means that even though this is a definition which involves an integral, so this is the integral from the initial position to the final position of the force dotted by our displacement, In this case, again, don't worry about this because we are not doing actual integrals, which means that for our purposes, we only care about two possible potential energies, and that's going to be gravitational, where gravitational in this case, I mean close to the surface of the Earth. So that potential energy is then mgy, where again, y is an arbitrary distance above some sort of reference point where we get to choose that reference point. And then spring, so our spring potential then is going to be u sub s is equal to 1/2 kx squared, where again, x is its distance away from the equilibrium position, which means that if I have an unstretched spring, then in this case, it's at its equilibrium position, which means potential energy in this case is equal to 0. Now, if I stretch it or compress it, so that now it's stretched by an amount of x, then this guy then has my potential energy, I'll do that in green here, of 1/2 kx squared. Or if I compress it, so here's my compressed, or again, this is my equilibrium position, so it's compressed by an amount of x. Then again, we get our spring potential then is equal to 1/2 kx squared. So it doesn't matter if it's elongated or compressed, the potential energy is basically the same. It's just the direction of the force would be different. But since we're dealing with energy, we just don't care, basically. So good. So now we have kinetic energy and potential energy, where potential energies then are the potential to do work. So these guys, again, can do work. So that brings us then to conservation of energy, where conservation of energy simply says that the change in kinetic energy plus the change in potential energy is equal to the work done by the non-conservative force. So for our purposes, a non-conservative force is anything that is not gravitational or spring, which means that things like tension, normal forces, whatever it is any force that is present, an applied force, etc. These types of forces can be non-conservative forces, where again, our non-conservative forces are things like, again, friction and etc. So again, anything that is not gravitational or spring. So these guys can be dissipative, they can be additive. But in most cases, as far as we're concerned, these guys are going to be dissipative forces. So this is basically going to be a dissipative force, or again, an additive force. Additive force. So let's see. Let's write down some steps before I move on. So steps to solve these problems are, again, step number 1, as we talked about before. So we're going to draw. And we're going to draw, in this case, the initial. What is it doing at the beginning? And then finally, what's it doing at the end? So the initial and the final positions of what this thing is doing. Now, most of the time, what happens in between is irrelevant unless there's friction. But basically, this is all we need to know. We only need the initial and then a final. From here, step number 2 is we're going to, again, identify changes in potential energy. So in this case, we want to look at, do I have any changes in potential? Meaning, do I have a change of height, which would be gravitational? Do I have a spring? Things like that. So, and then from there, we want to determine which kinds. So again, is it gravitational or is it spring? Step number 3, then we want to identify non-conservative forces. So do I have friction? Do I have a tension? Do I have an applied force? So I have anything that is either adding or subtracting energy from the system. So if I do, for example, if I have friction, then in this case, my non-conservative force, for example, so this is an example, would be my work done by my friction, which is then going to be equal to my friction force times then the displacement at which the force, in this case, my friction force is acting, times cosine of the angle between the two. And of course, if this is my object, my displacement would be in this direction, while my friction force would be in this direction. So in this case, the angle between the two would be 180 degrees. So this guy would be equal to minus Fk delta x, again, for an example. So determine and identify any non-conservative forces, and then determine exactly what the work done is by that guy. Step number 4 then is to apply our conservation of energy. And then finally, step number 5 then is going to be, of course, solve for whatever it is that I'm actually looking at here. So, good. So in this case, what do we want to know? So again, applying our conservation of energy, we're just going to put all of our stuff together, which says our change in kinetic plus our change of potential. Now, again, if I have more than one potential, I have to make sure I add all the different types of potential. So for example, if gravitational potential energy and spring potential energy show up in the same problem, are then equal to the work done by the non-conservative force. So split up the potential energies. And then solve again, we're just going to solve for whatever it is that we're looking for, either the velocity or compression or whatever it is that we have to do from there. Now, one other thing I'm going to put on here, and I'm going to put this as a asterisk on here. So always choose the simplest way to do it. So the simplest method, which means if you can do the problem in one beautiful, glorious step, do that. There's no reason to actually split it up if you don't have to. So that'll just basically save you some time. Good. So from there, what else do we have? So we have the relationship between the force and the potential energy is minus the derivative of the potential energy with respect to position is then equal to the force. Technically, this is again a gradient, but we're not going to worry too much about that. Now, since we are going to have derivatives, so we will have derivatives. So this is completely on the table. We will have derivatives. So those of you in Calc 1, you are doing derivatives now. So this should be nice and easy, but we haven't, in Calc 1, you're not in integrals yet. That's why we're not actually doing integrals. Besides that, we also know that the total energy is going to be equal to a constant as long as we have no non-conservative forces. Which means that this is equal to the kinetic energy plus the potential energy at any point, right? Which means that our kinetic energy then is going to be equal to the total energy minus the potential energy at that point. So in this case, we're talking primarily about potential energy versus position plots. So again, if I have something that looks like this, and this is, say, my total energy, then as this object is moving, let's say there's an object here, as this guy is moving in this direction, since potential energy in this case, as I go further and further, is decreasing, that means my kinetic energy is then increasing. So until I get up to this point here, which is what we call our turning point. So remember, our turning point is defined in the fact that the kinetic energy is equal to 0, which means our total energy then is equal to the potential energy at the position of the turning point. What else do we know? So we also know that we have equilibrium positions. I knew how to spell. There we go. Equilibrium positions. So all our equilibrium positions are defined as the derivative of the potential is equal to 0, which means that there's 0 force acting on it there. So for example, this is a equilibrium position. So this is where my derivative is equal to 0. This is also an equilibrium position. This is also an equilibrium position, and etc. So in all these places here, the force on the object is simply equal to 0. Now, the difference between each one is whether I have an unstable, which is what this one and this one are. So these are unstable equilibrium versus this guy here, which is then a stable equilibrium. So what determines the fact of those is the second derivative test. So if my second derivative at the equilibrium position is positive, this is what we call a stable equilibrium. And then if our second derivative at the equilibrium position is negative, then this is an unstable equilibrium. Right? So good. So this is when we're talking primarily again about these types of plots here. So a position or a potential versus position plot. After that, we have revisited power. So power is exactly the same thing. So I'm just going to leave that the way that it is. So that's our energy chapter. And then finally, we have our momentum chapter. So let's talk about momentum. So again, momentum by definition, P is equal to mass times velocity. So again, this is a weighted velocity, basically. So again, the more massive an object is, the more momentum that it has, even if it's moving at the same speed as another one. Let's see here. Now, in this case, since this guy's a vector, this means direction matters. Unlike energy, where it's a scalar quantity, so it doesn't matter what direction it's actually moving. But since this guy's a vectorial quantity, it does matter the direction that it's moving. So you will have to set up some sort of coordinate system and then pay attention to the direction that it's moving relative to the coordinate system. And then that determines if it's positive or negative. We have our total momentum, which we call capital P, is then equal to the sum over all the individual momenta. Good. So that's this guy. From there, we then also have that what? That the impulse, let's do the impulse. Impulse then is equal to the integral from the initial time to the final time of the force integrated over time, which is approximately the same thing as the average force times my change in time. Now, by the impulse momentum theorem, then is equal to the change in momentum for a single object. Or if I have a system or a more than one object, then this is equal to the change in the total momentum. Now, from here, if the total force, or the external force, I should say, acting on my system is equal to 0, then in this case, this tells me that my change in momentum must be equal to 0, which gives us conservation of momentum. Fantastic. So all this means then is that my initial net momentum must be equal to my final net momentum. Now, when it comes to momentum, we mostly only care about momentum when it comes to collisions. So let's talk about some collisions. So collisions, again, we have three different types. We have what's called the elastic collision. And this is when the change in kinetic energy is equal to 0. Now, in this case, this is actually the change in total kinetic energy, not just the change in kinetic energy of each object individually, but the sum of all the changes of kinetic energy. So this, again, as we drew in class, is when I have two objects where this has a mass m1, this has a mass of m2. This guy is, say, moving in this direction with v1 initial. This guy then is moving, say, in this direction with v2 initial. Good. And then after the collision, these guys bounce away from each other so that now this one's moving in this direction with v1, sorry, final. And then this one's going to be moving in, let's see, what color haven't I used yet? We'll use blue in this direction with a V2 final, right? Now, again, the change in kinetic energy for each one of these objects may not be 0, but the total collection is equal to 0, which also means that what? The change in momentum for this object here will not be 0. The change in momentum of this object will not be 0, but the change in total momentum has to be 0. We also then have number 2, the inelastic collision, which says that the change in total kinetic energy is negative, so it is not equal to 0. So the picture here looks exactly the same. So this picture is the same. The only difference is that energy is lost during the collision, typically due to some sort of deformation, and the fact that the object doesn't rebound exactly to the same shape it was before, so there's energy lost in there. And then finally, we have what's called the completely inelastic or perfectly inelastic collision. Which says that, again, my change in kinetic energy total is less than 0, but it's drastically less than 0. In this case, the only difference is that my final picture looks like these two objects stuck together and then moving in one direction with a final velocity of v. So in this case, the final momentum would then just be equal to the sum of the masses m1 plus m2 times the total velocity at which it is that they're moving. So good. So the first part of the picture, color that here, stays the same, but then the final picture becomes this guy. So good. So good. So these are my three different types. So the strategy for solving these problems, again, let's look at our steps here. So let's do our steps just like before. Again, step number 1 is the same thing. So we're going to draw. And when I say draw, I mean draw and label everything. So make sure you get all your velocities and all your masses with the directions, because again, direction matters. So we're going to do this for both the initial, so before the collision. Actually, let me do it as before. So let's do this before the collision, and then also after the collision. Step number 2 then is going to be, again, basically what type of collision do I have? So do I have a inelastic collision? Do I have a completely inelastic collision, or do I have a elastic collision? So in this case, once we know that, we can then apply conservation of momentum. Step number 3 then is going to be, and this is, I'm going to do this in red here. This is only if it's elastic. So if it's an elastic collision, then we have to apply conservation of energy as well. Energy. And then step number 4 is basically the same thing as before. We're simply going to solve. Right? Oh, let me go back to my collisions here real quick. Sorry about that. So in all 3 of these collisions, even though energy is only conserved in elastic, for all of these, the change in total momentum must be 0. So for all of them, momentum must be conserved, but energy itself is only conserved in the elastic collision. Sorry, I forgot to write that down. So great. So that's basically that. So again, you're going to draw. When you draw, you make sure that you label everything. So again, if I have both objects which are moving in the same direction, if I call this my positive x direction, and this is say M1, and then this is M2. So I want to make sure I draw. So this is my V1 initial, and then this is my V2 initial. So make sure I draw those things on there. And then this is my before picture, and then my after picture, I might have what? This is M1, and again, this is M2. So let's say M1 is catching up to M2, but it's less, or I mean, less massive than that of M2. So this one's going to say rebound in this direction. So this is going to be my V1 final. And then this one's going to gain speed. So it's going to be moving with a slightly faster velocity. Let's call that V2 final. So again, in this case, this one would be a negative momentum, right? So I get a minus momentum because it's moving in the negative x direction, where this one then, actually all the rest of these guys would be positive momentum. So good. So that's pretty much about it. Now, as I mentioned in class with these guys are pretty much always going to come with energy conservation, but let's get to that in just a second. Now, for an elastic one, what we found in class was that a one-dimensional elastic collision, the final velocity for the first one is then going to be equal to the initial velocity of the first one times the mass of the first minus the mass of the second, plus twice the mass of the second times the initial velocity of the second, all then divided by the sum of the 2 masses. Where the final velocity of the second one is then going to be equal to the initial velocity of the second one times the mass of the second minus the mass of the first, plus twice the mass of the first times the initial velocity of the first, divided then by the sum of the masses. So if I have a 1D elastic collision, go ahead and use these automatically, so you don't actually have to apply these 2 steps because we already did. But if it's a 2-dimensional collision, you will have to do that. So in this case, you'll have 3 equations with 3 unknowns. So as I said, basically what happens is that conservation of momentum will never come by itself. So what do I mean by that? What I mean by that is, for example, if I had, let's say, a plane that had something like this, where I start off with a mass of, say, M1 on here, this guy's going to slide down, and then it's going to collide then with some other mass of M2. So basically what's going to happen in this problem then is you would have to split this up, unfortunately, into multiple places, where in this section here, you would have conservation of energy, right? Because I have to find out what is the velocity of M1 right before it hits him. So this is going to be my V1 initial. And then I'm going to have the collision. So during this section here, we're going to have then conservation of momentum. And then after the collision, whatever happens then, so the after portion, we're going to have conservation of energy again. So in any problem involving momentum, it's pretty much going to work like this. So you're going to have some sort of energy conservation followed by momentum. So some sort of collision followed by conservation of energy again. So you'll just have to work out the problem this way. So unfortunately, in this case, you will have to split it up, even if it is an elastic collision. And this goes back to what I was saying earlier, which is going back to here. Even if I have an elastic collision, the change in kinetic energy for each individual object will not be 0. It's only the total energy. which means unlike in conservation of energy, where we can do everything in one beautiful, glorious step, we can't do that here because, again, when I'm looking at each two of the different objects, even though the total energy is conserved, the energy within inside of each one of the objects is not conserved, even if it's elastic collision. So even if it's elastic, we do have to split this guy up into these guys. So that's pretty much about it as far as all the equations and stuff are concerned. So let's talk about what to expect. So what types of problems? So types of problems are a number one. So there will be a conservation of energy problem. So just conservation of energy. Number two, there will be a work kinetic energy problem. So I will have you specifically do it using work kinetic energy theorem. So meaning if you don't use work kinetic energy theorem and you use conservation of energy, you will not get full points for it because you didn't do what I asked you to do. So even though you might get the same correct answer at the end of the day, which you obviously will because work kinetic energy and conservation of energy are basically the same thing. But since you didn't quite follow directions, you will not get all points if you do it that way. Number three will be the potential versus position. So going again back to these guys here. So it'll be one of these plots here, and I'll ask you a bunch of questions or some questions about things like the force, possibly the kinetic energy or the velocity at a point, where, say, the turning points are, where the equilibrium are, things like this. So keep that in mind. And then the last one will be conservation of energy and conservation of momentum. So that goes back to this types of problem I'm talking about here. Well, we'll have, say, something happens where you have to use conservation of energy, again, in this first part here. And then you'll have a collision, which means you'll have the second part. And then after that, you'll have conservation of energies, again, which means that you'll have some sort of third part here. So these are the four types of problems that you want to get ready for. So conservation of energy by itself, where there may or may not be a work done by a non-conservative force. The work kinetic energy theorem, where again, I will specify that you have to do it by work kinetic energy theorem. So again, if you don't use the work kinetic energy theorem, you will not get full points for it. And then a potential versus position plot, and then finally conservation of energy and conservation of momentum problems. So that's pretty much about it. So yeah. So these are the things to look at. These are the things to be ready for. And other than that, and have a great time. So anyways, I'll see everybody tomorrow for the exam.